Live. You're live.
But I don't, she didn't tell me anything.
All right, so on our schedule, we're going to talk about the next section, which is basic probability, and then we're going to have exam number 2 for the second part of our class. It's certainly possible that if you had any kind of a question about anything regarding exam number 2, I'd be happy to answer that question right now. So does anybody have anything that you need to know regarding exam number 2? Yes.
So on the practice exam for number 7, I understood that like the empirical rule wasn't gonna work for that problem because it wasn't bell shaped. But what did you mean when you said the bottom end is too low?
Okay, so that when we look at that particular problem, then it has to do with the fact that the empirical rule is supposed to be symmetric. Okay, so if we look at the data set here for practice test number 2, okay, then when we set this up, it goes from 8 to 29, right? But then when we do the empirical rule, the empirical goes all the way down to 1. So then the empirical rule goes way farther below our data on one side, but it's pretty much at the top of our data on the other side. So then the empirical rule does not actually reflect how the data is distributed. So in that sense, it's too low because it's farther below what we would expect it to be.
Okay.
All right, that's a great question. All right. Anything else? Yes, question.
When you say top 3, what is that?
Top 3. That means the 3 data values that are the largest.
And then for our answer, do you want us just to say something as brief as that, or do you want us to like?
That's really up to you. I don't mind either way.
Okay.
All right. All right, any other question about anything on test 2? All right. Something else comes up, feel free to let me know. But for right now, what we're going to do is work through the information on chapter 4, which is dealing with probability. And we'll try it without actually reference those things in specific. So what we need to work on here, see if I make sure I get on the video side. Well, we're all the way over here, okay? I want to know the purpose of statistics. Yes, Cameron.
Making data-driven decisions.
Okay, data-driven decisions. Now somebody else tell me, what does that mean?
What to expect, trends and information.
Okay, so we've got what to expect, which includes trends and information. What does that mean, what to expect? Somebody else tell me what that means.
Anything below 5% of that is unusual.
Okay, so anything below 5% chance, we kind of say no. And then what's the rest of it?
Above 95%, yes.
Okay,
And anything between that is maybe.
okay. All right, so we have things that we would consider to be unusual. We would say they would surprise us if they happen. We have other things, they surprise us when they don't happen. We have everything else. Now, there's something besides statistics that we have to include in this process. Can somebody tell me what that is? We have to have experience. And then there's something else. Alex?
No, the meaning of the numbers.
No, that's what experience tells us. Experience tells us the meaning of the numbers, but there's another thing besides experience that we need. I think I mentioned it. Right?
Is it humility?
It is humility. And that's really the topic for today. What do we mean when we say humility? What we mean is that we do not actually know what's going to happen, and we cannot actually know what's going to happen. So if someone says to you, let's say that you're a doctor, and somebody says, okay, so you're telling me that if I take this medicine, I will get well. As a doctor, you should say, well, I can't tell you absolutely for sure that it will. There's a lot of different things going on here, but I'm doing it to try to help you to get well. I'm not saying that this thing will absolutely positively get you well. That would be humility, because you don't want a person to think that they can just follow your directions and that everything is going to turn out okay, because it might not, and you don't know for sure. So you tell them that so that they're prepared for the possibility it might not work. And depending on the treatment, it might be more sure or less sure. The same thing is true for pretty much anything, okay? And so then humility will not say that something is absolutely for sure if it is actually not for sure. So then, this is related to the idea of probability. A way to describe probability is understanding how to deal with uncertainty. And specifically, using math. So we're going to apply mathematical ideas to situations where we are not certain of what's going to happen. And as I said at the beginning of the term, a lot of times when you do math, you do know for certain what's going to happen. If you get the right answer, it's going to be a certain right answer, and everybody who gets it right gets the same answer. But that's not how it works in probability all the time. So we need to kind of understand what's happening here when we talk about something that might happen or it might not. And this is the basis for our 5% and 95% ideas, that 5% is a probability idea. That's what we're talking about. So then we're going to define probability in a specific way, but let's just talk about a situation, for example, how many of you have recently played a game where you had to roll a die or dice? Not very many of you. Okay. It's kind of going out of favor, but how many of you have ever played a game where you had to roll dice? Okay, that's everybody, pretty much. So then you know how it works, even though you might not have done it recently. Okay. So let's say that you're playing a game, and if you get a 6, then you win. This is how probability works. You don't actually know if you're going to win or not. You're going to roll the die, and you're going to see what happens. You don't know the outcome. But the question is, how surprised would you be if you did roll a 6 and win the game? Well, that's kind of a subjective thing, right? But if you've had experience rolling dice very much, then you would not be totally shocked to win the game. It could happen. It may not be the most likely thing, but it could happen. So what we're going to do is we're going to describe how to understand this in mathematical sense. So then what we're going to say is that the probability of something is equal to the number of items in a specific set divided by the total number of items. It's not a difficult formula, but sometimes the concepts are difficult because we have to make sure we know what we're talking about in terms of members of a set. As it turns out, all of mathematics is based on set theory, but probability is even more clearly based on the idea of a set. So, how do I know my chances of getting a 6? Well, I'm going to change this. Sorry. I'm going to change this to a 5. Just make sure it's clear. So there are some games where you have to land on the thing and you have to land exactly on it. So you have to get a 5 on the die in order to make that happen. So if I ask the question, what's the probability of getting a 5? Can somebody tell me the answer to that? It is. Now what I want you all to do is to put that on your calculator and tell me what happens when you do that. So Luann, did you do that? Did you put 1 divided by 6 on your calculator? What'd you get?
0.1.
Okay. So then this would be the fraction form of this probability. If we do it in decimal form, it's 0.1 and then 6 repeating. What would it be in percent form?
16.6.
Okay, 16.6 repeating, right? This is very important because most of the formulas that we use in probability are done in decimal form, but you need to understand them in percent form, okay? So you understand percents, but you also understand them in decimal form as well. Now, if I were to say, what is this actual answer? I don't want to say 16.6 repeating because I don't want to go out that many decimal values. I just want to round this off. So what would be a reasonable answer to this? 17. And it'd be 17%. So that's pretty standard. If we round off to a percent, it would look like this. But what if we wanted to round off to the nearest 10th percent?
$16.7.
16.7%. Okay. It does not mean to the nearest tenth from the decimal, it's the nearest 10th percent. So you need to know how that works. I think there's some problems on the homework where you need to know that. So then, now we look at this and we say, is this a no? It is not. Is it yes? No. Is it a maybe? Yes. That made a lot of sense, right? Okay, so this is a maybe answer. If before you roll the die, you say, am I going to win this game? The answer would be maybe. And then if you say, well, it's relatively low probability, you could say maybe not, because it's pretty low. But you would not be shocked if you actually get this thing to happen, because it's a 17% chance, and those things happen. And most people are aware of the fact that if you roll a die and you need a number, you could get that number, and it would be like a happy thing, but you would not say, oh, wow, I can't believe. No, it happens. So that's how you understand it. Now, when we do this, the way we actually write probability is using this particular form right here. And sometimes people get confused by this. This is not the letter P multiplied by the letter 5, or the number 5. This is, the 5 is a label telling me what probability I'm talking about. This is the probability that the number 5 comes up. For example, it looks like the clouds are kind of going away today. So we might say that the probability of rain might be something like 20%. This is not the letter P multiplied by rain. This is the label, rain. And so it's the probability of that thing happening. If you've ever done functions, this is a function. If you haven't, it doesn't matter. You just look at it and you say, okay, this thing, the P with the parentheses, the thing inside the parentheses is telling me what event it is. And then when I put the P with the parentheses, I want to get the probability of that event to happen. So then, there is something that goes on here, though, once we start talking about the situation. And that is, are there actually things that happen completely by chance? Or are there not? And this is something that we have to kind of put in the back of our minds so that we don't get too affected by the idea. There are some people who have these ideas of like karma or fate or something, where it's like, well, if you kick your dog in the morning, then you'll have a car accident at night or something like that, right? And then there are people who say, well, everything's connected. Similar idea. Then there are people who, from maybe a religious standpoint, they would say, well, actually God's in charge of everything. And when something happens, then it could be that God is actually making it happen and it's not just by chance. But the fact is, no matter what your perspective is, you don't actually know what's going to happen. So if it's, if God is in charge, then that can have a different religious meaning for you. But it's also true that when you roll the die, most likely you're not getting a direct communication from God telling you what's going to happen. Not that that'd be impossible, but that's not how it normally works. When we say as we go through our lives and we see things happen and we say, is that a random chance? If it is not a random chance, I still don't know the answer. And so I'm going to treat it as though it were a random chance. Even though it might not be, I don't have enough information to think otherwise. So if I'm going to sit here and roll this die 100 or 1,000 times, I most likely do not know what it's going to be every time. And so then I'll just go with what I see as the pattern of how the thing is actually happening. So it's an understanding of how things work and kind of the patterns that we see in our lives, regardless of whether there is actually some other outside influence making them happen. We ourselves have humility because we don't actually know the answers. Even though there might be clear answers, we don't know them. So then we have to say we don't know. All right, so then we have, when we start to talk about how this works, this is an example, this first example that we have, when we talk about types of probability. The first type is called classical. The second type is called observed. And the third type is called subjective. And all three of these are important to us because all three of these are a part of what we measure in statistics. The first thing is classical. In that situation, we say every outcome has an equal chance. Would you say it's generally true that if you roll a die, that all 6 of the possibilities are the same chance? Does that make sense to you? You roll the die, it could be any number from 1 to 6. Most of the time, you say, yeah. How about flipping a coin? Is it 50-50? Well, actually, there was a couple of times when I would flip a coin and I dropped it. And so then it fell on the ground and rolled away. So maybe not exactly. I don't know if in like the Old West, when somebody would try to flip a coin and somebody would shoot it out of the air. So that might happen. So generally, though, we have certain things, and we talked about the raffle, right? If you have 100 tickets in a bag, you shake them up, you figure they're evenly mixed up. That kind of thing. But then we have a different kind of probability when we go to observe. In this situation, we're looking at the number of items divided by the total, but we're not thinking just as all the different possible things. We're saying, I want to find out by observing. And this is the kind of thing that would happen in a survey. All right, so how many of you had fruit juice in the past week? 1, 2, 3, 4, 5, 6, 7, 8, 9, 8, 10. So that's 10. Out of, and let's just ballpark it, let's say there's 30. What's 10 divided by 30? Okay, what percent is that?
33.
33%. So that would be our empirical or our observed probability of somebody having juice, the juice drinkers. So this is not something based on like rolling a die or flipping a coin. It's actually asking a question. How many people out of the total would have this particular characteristic? Now we have to be careful about this though, because what we're dealing with here, this is a sample, right? since I only asked 30 people, I didn't ask everybody in the world, okay? If I want to say that this is true in general, I'd have a problem because this number will have, it's a sample, it has sampling variation. It won't always be the same. When you think about rolling a die, what are your chances of getting a 5? You say, okay, that's always going to be true. If you have a regular die and you roll it, it's 17%. But this, fruit juice drinkers, that's going to be changing. It's going to be changing because you're just taking samples, but it's also changing just because people change, right? A year from now, if I ask the same question, you might not have the same answer because your juice drinking habits could change. So this is an observed probability, which is not always going to be the same answer. Now, a subjective probability is based on experience. What do you think the chances are that there is somebody out in the hall right now?
What?
What do you think?
20%.
Okay, relatively low. Okay. Nobody. All right. Why did you say 20%? Why did you say it was going to be low?
Probably faster now.
Right. Time of day. So what if I were to go down to the Union Market at noon? There's probably going to be people down there. Yeah, okay. So that's based on your experience. You know that this is not really a busy place in between classes during this time of year and this time of day. So you're not surprised to walk out there and there's nobody there. You don't know for sure, but based on your experience, you'd say the probability is low. What are the chances of having like 10 people walking down the halls of Western that have the same color shirt on? So what do you say?
5%.
Okay. If you had my experience, you would know that there are certain programs where they all wear the same color shirt. And so then you walk by them and all of a sudden, oh, there's a bunch of people and they've all got the same color shirt on. But you haven't had that experience, you wouldn't know that, right? So it's subjective. It's based on what you've actually been through. And that's how people think regarding doing research. If you're going to do research on something, you have some kind of an idea about what thing happens a lot and what doesn't happen a lot. And so then you go out and you try to measure that thing because you think it's either important or there's differences somewhere, but that's based on your experience. And so then when you combine these things together, then you say, all right, we have different kinds of measurements that we do, different kinds of observations that we see, but how would we compare that to what somebody else observed? Those kinds of things. Now, when we do this, there's something called the law of large numbers. The law of large numbers tells us that for large samples, observed will get close to the class. So if I roll a die, $6,000 times, I would expect 5. How many times? Not exactly 1,000, but close. So if I roll this die 6,000 times, I would expect a 5 to happen 1 out of 6, but not exactly. I would not be shocked if it was, 993 or something like that. But if it was 17, I would be completely shocked. How is it possible? This is just not possible to happen. But for large numbers, we would expect that it's going to get close to the classical result. But then we have to deal with another issue here, and that is gambling. The gambler's fallacy. There are 2 ways that this can happen. Sometimes people get the idea of what will happen if they lose a lot. But first of all, we have to think about this. Why does somebody even gamble? What's the point of gambling?
Win money.
Actually, no.
Spend money.
But for what end? What do they want to get out of the gambling? They're not going to get rich gambling,
Right?
but they might. Okay, so what is it that they actually get? That they definitely get from gambling?
Satisfaction.
What kind? Is it like, well, I got a ribbon and I like pretty ribbons? Probably not.
Like they feel hot. Like sometimes you describe gamblers, it's like they describe themselves as feeling like a high.
Okay, there is a thrill or a pleasure that's involved. And as it turns out, we all have this experience. We just don't all use it in a gambling setting. And that is that if there's a chance of something happening, it heightens our senses. And so then we pay more attention to it because it might happen. And then if it does, then we really feel good. And if it doesn't, we still had a high level of emotion and commitment to it. This happens on roller coasters, when you're watching movies of various kinds, dramatic tension, even listening to certain kinds of songs, that you're thinking about something and then all of a sudden you're expecting something to happen and something else happens. You're like, wow, that is a different thing. So it's a psychological feeling that's actually based on how less likely the thing is to happen. As it turns out, people prefer to gamble when the odds are low as opposed to high. People expect to gamble when they run more of a risk because that's more of a thrill when they win. Who's going to put all their money on the favorite horse to win? Well, there might be some people who do. But there's going to be a lot of people who are going to put their money on somebody else because if they win, it'll be just so amazing. So it's the psychology that's really about this. So the gambler's fallacy is based on two kinds of psychology. The first one is, if you lose a lot, what do you think is going to happen? I lost 15 times in a row.
You're gonna win big.
So then you think you're going to win. And sometimes people think that's what we're talking about here, that everything has to even out in a certain amount. So if I lost a lot, I've got to win because it has to kind of even out because of statistics. That's not actually true, okay? That's not how it works. Every different outcome is its own thing. So just losing a lot doesn't actually mean you're going to win the next time. It doesn't work. Okay. However, what do people think if they win a lot? As it turns out, they think they're going to win because they think they're on a hot streak. So it doesn't matter. You lose a lot. Oh, I'm going to win next time. Sure, yeah. You win a lot. Wow, I am winning so much. I am going to win more. And it's not logic, just based on psychology, right? You want to win, and you come up with reasons why you think that you're going to win. Now, there are situations like, for example, if people are playing basketball and somebody is hitting all of their shots, they might gain more confidence and actually shoot more. And because they have more confidence, they'll actually score more points. So it does happen. And then sometimes it doesn't, right? Where they get a lot of confidence and they just keep clanging. Sometimes that's how it goes. All right. So these are some ideas in these different kinds of probability and how they relate to one another. But one of the big things in making this happen is that we have to be able to count these things properly. We have to count the number of things that are happening, and that's not always easy. So what we're going to talk about is something called a tree diagram. What does a tree diagram do? Well, it's a way for us to show a specific idea in probability, and that is every choice will multiply the options. So let's say I flip a coin and then roll a die. What does that look like? Well, the first thing when I flip a coin, I can get either heads or tails. And so I make two branches. And then when I roll the die, that gives me 6 options if we're talking about a standard die. So then if I make a list of all the possible things that can happen here, I'm going to end up with 12 things. Because I have 2 options for my first choice, and then I have 6 options for my second choice. That gives me a total of 12 options. So this is how it works. When you make another decision, you have to multiply the things that can happen. So when you make a list, I won't take the time to make the whole list, you would get 12 different things. All right, so let's think about how this might work. let's say I go to, I don't know, if people go to McDonald's still? I think they do, so let's say go. And what you're going to get is a sandwich, a snack item, and a drink. How many possible sandwiches can you get at McDonald's? It's been a while since I've been there, but somebody give me a decent number here.
20.
20, all right, we got some agreement. How many little snacky kinds of things? Well, I can think of fries, but I'm sure there's more than that, right? Fries, apple slices. 10. How many different kinds of drink are there at McDonald's?
There's probably 20.
Okay, say 20. So what happens when you walk into McDonald's? How many choices are possible? We're going to multiply these numbers together. What's 20 times 20 times 20?
4,000.
Now, I have some family members that have dealt with various mental health and anxiety issues. And one thing that happens is when people walk into something like McDonald's, they consider that there is one correct option out of those 4,000. Because there's one sandwich with a certain snack and a drink that would be the optimal, the best possible thing to have. And they feel pressure that they have to find that best option. And they have to think through all 4,000 possibilities. Well, it's going to take a while, right? So then when you get to a point where you have so many possible things you could do, that doesn't make it easier necessarily to give somebody a lot of choices. It can make it even more difficult to choose, right? But that's how it works. That's how many things are going to happen. So you're going to have a lot of those things out there. So then what we would want to do is we would want to pick the number of items in the specific set out of the total number, and that total number we got by multiplying like this. So let's do a situation where we have 2 dice. And if I ask the question, how many outcomes are there? How many possible ways can we put 2 dice together? What would you tell me? 36? There would be 6 on the first one and then 6 on the second one, and we'd multiply those together. What we have to realize here is that the order is actually important. And I didn't know this for a long time until maybe like a couple of years ago. I finally figured this out. If you're going to roll 2 dice, a 1 and a 3 is different from a 3 and a 1. Even though you might not be able to tell by looking and say which one it was, they are actually 2 different dice. Certainly if you have a red and a green one, it's obvious that a 3 red and a 1 green is not the same as the other one. But the fact is they are different. So the order is important. And we talked about how this works. So what is the probability of getting a 3 when you roll 2 dice? Well, how many different ways can you get a 3? Okay. So there are 2 of these, and there's 36 total. So what's that probability?
5%, or like 5.5.
So you would say 6%? Okay. About 6%. That's pretty much what we would call unusual. So if you're rolling 2 dice and you have to get a 3 to win the game, you would be surprised if you got it the first time. Whereas if you just roll 1 die, you're not surprised. If you roll 2 dice and you get a 3, that would be surprising. Now a 7 is more common because there's more ways to do it. A 12 would be hard because there's only 1 out of 36. So this is how we kind of judge what is more or less likely to happen. We have to make sure we can count the number of outcomes and then decide how many are in the specific set. Question?
You're saying a total of 3, not just
A total of 3, yes, because I'm rolling 2 dice. Yep. All right, now there's a couple of other things that we need to talk about. The first one is that probability has to be between 0 and 1. If I say, what's the probability of getting a number on a die? Well, I'm always going to get a number. So then this would be 6 over 6, which would be 1. But if we express it as percentages, it's between 0 and 100%. So you need to be aware of how this works. 100% is the same thing as 1. Because as a decimal, it would be 1.00. It's the same thing. Then we have another idea. If my probability of winning is 6%, what's my probability of losing?
Four.
94%. This is called the complement. I might win, but I might lose. But the idea is there's only 2 things that can happen. And when we say, how do I know what these are? They have to add up to be 100%. But the actual formula looks like this. Again, writing it not as percentages, but as decimals. So this would be 0.06, this would be 0.14. Probability of something not happening is 1 minus probability of the death. Now, if we have a tree diagram where the things that are happening are not necessarily equal every time, I'll show you how that would work here. Let's say I have 7 socks in a drawer. I have 5 blue and 2 red. Why I would have single socks in my drawer, we're not going to worry about that right now. We're just going to say this is what's happening. This is how my dad ran his life. His socks were all the same color, And so they need to put them in a drawer and just take them out. Didn't matter. Solving all that, putting the socks together and stuff. But I actually have socks of different colors, believe it or not. This person has blue and red ones. They've got 5 blue ones and 2 red ones, and they're sitting in the drawer. And what we're going to do is take out 2 socks. But when you say, how does that work? How can you take out 2 socks? You would take out one and you would hold it. And then you would take out the other one. This has a technical phrase, without replacement. If I want to actually have 2 socks in my hand, I have to take out one and not put it back in. So that's without replacement. So I want to start by considering what are the different options here? What can I do? Now I could make 7 branches, but I'm going to instead just have 5 that are blue and 2 that are red. In your mind, there's 5 of them here and 2 down. So then the question is, what happens when I take out a blue sock? I'm sorry, what?
There's 4 blue left.
There are 4 blue left, so it changes the drawer. I used to have 5 blue and 2 red. But when I take out a blue one, it makes the drawer look different. So now it's 4 blue and 2 red. A similar thing happens if I take out one of the red socks. After I take out a red one, I have 5 blue and 1 red. So then when I look at the situation, again, I'm looking at the drawer, I list all my options. I then take out a sock, and I'm looking at the drawer, and I'm just listing the options. So then in order to know my options, I have to look at the drawer and write these things down. So then the situation is, what happens if I want to then take out my second sock? I'm going to multiply as I go from one choice to the next. So when I say, how many ways can I have blue, comma, blue? That would be 5 multiplied by 4, which is 20. So again, as I go from one choice to the other, I multiply the different choices. You could have 5 different branches here, and then each one of those has 4 branches on it, so that makes it 20. What about blue, comma, red? That would be 10. What about red, comma, blue? That would also be 10. How about red, comma, red? That would be 2. So how many different things can happen here? What's my total number of outcomes? If I add all these up, I have 42 outcomes, which makes sense because I had 7 socks to begin with, and then I had 6 socks the next one. So I started with 7, and then I took one out. So my first drawer had 7, my second drawer had 6. That means I have 42 different options. So this is how it works. Now, if we wanted to, we could figure out the probabilities for each one of those. We won't take the time to do that. But what we are going to see here is that we could figure each of these probabilities not just as 5 socks, but as 5 socks out of 7. So I write it like this. instead of saying just 5 socks, I'm saying 5 socks out of 7 in the drawer. And then what happens next would be 4 socks out of 6 in the drawer. And this would be 6. So this is why probability tends to get a little difficult for people. Situation like this, where they say, okay, how am I supposed to know what's going to happen or what might happen? If we have the idea that these different things multiply as you go, hopefully you can see that they multiply, then we can also take these probabilities and multiply them. Because if I say, what is my chance of getting, for example, 2 blue socks? What's the probability of getting blue, comma, blue? That would be 5 over 7 multiplied by 4 over 6. And that's a number. Anybody got a percent for me on that? Okay, so let's say 47. Now you can see this if you look carefully. This is 20 out of 42. This is also 20 out of 42. So when we're looking at situations where we are doing separate choices, and we ask the question, what are the probabilities of this thing happening? We multiply as we go. This is the multiplication rule. So that when I say I want this to happen, and then I have a separate thing which also happens, I multiply those probabilities in order to get the answer. And then I think we're going to try with one last thing. If I ask the question, what is the probability of a matching pair? What's the probability that the socks will actually be the same color? Well, I have 42 options. How many of my options, if I'm looking at this right here, how many of my options have the same color? 22, because it's blue, blue. It's also red, red. So this would be 22. And so what that gives us is the addition rule. if I'm looking at my collection of things and I say, well, I want this, I also want this over here. The specific word that's used in statistics is the word or. So that I can have 2 blue ones or 2 red ones. It doesn't make sense I would have 2 blue ones and 2 red ones because I can only have 2 socks. So I could have 2 blue ones or I could have 2 red ones. And when I say, what does that actually mean? I add those numbers together. So I'm adding probabilities when I have this word or. Now, the use of the formula is not as important as the understanding of the process. You don't have to memorize these formulas. You don't have to draw a tree diagram. But you need to understand how the probabilities can be combined so that you know the difference between I have this and then I make another choice and that multiplies versus I have all these things that could happen and I want to consider them all included together where I would add those probabilities. So I'm going to allow the homework to be your way of exploring this further. And we're going to take a break for 10 minutes. So it's 1:44. We'll come back 1:54.